All right, so today we're going to talk about the product rule. This is a new rule in calculus that kind of expands on what we've already been doing, but shows us how we can actually find the derivative of a function that contains something times something else. Let's get going. So first things first, today's plan, we're just going to begin with a quick review of yesterday's power rule plus a challenging question. It's not going to be anything super extraordinary, but I just do want to kind of push us a little bit further with this. Then we'll introduce something a bit more challenging, but every bit as useful. It's the product rules. Then we'll do some various problems and, of course, some practice. Now, I do want to remind you, we do have a quiz on Monday coming up here. So we have today, tomorrow, and then the next day of review, of course. It will cover the definition of the derivative, so those really annoying limit-based questions, you will have to do one of those, unfortunately. But most of it is the power rule, product rule, as well as the topic that we're going to be doing next class. Anyway, we'll worry about that as that comes closer. Let's get started. So just a reminder as to what the derivative is. Recall that the derivative of a function, which we always denote as being f prime x, represents a new function that outputs the slope of a line tangent to the curve of f of x at a given value of x. In total plain English, because that was quite a sentence there. In total plain English, basically, it's like, all right, you can get a derivative, which is a new function, that when you plug in some x, like let's say x is -1, you can find what the slope would be at that point, right? So the new function just tells you what the slope is of that original function at any point x. So this function here that we see is negative x squared plus 4. Find the derivative and then find the slope of the tangent for when x is -3, 0, 3, and 5. So first things first, if we're going to find the derivative, let's just use our good old-fashioned power rule here. It's not too bad. So f prime x, that's the derivative of f, equals, if we use the power rule on this, we just have to take the exponent and drop it down out in front. So that makes it -2, and then that'd be x to the power of, we drop this down by 1, so x to the power of 1. That's all well and good. But then we also have to take the derivative of this plus 4. Well, you can think of this 4 as being like 4 times x to the power of 0, because x to the power of 0 is just 1, right? So it's just 4 times x to the power of 0. If the 0 drops out in front, boom, the whole thing's gone. It's just 0. So guess what? The derivative of this function is just -2x. Or if you really prefer, you can say -2x plus 0. But that's obviously not doing anything, right? All right, so if we're going to find the slope of the tangent for these 4 points, let's just plug them in, right? So this will be f prime -3. That just means we plug -3 into our function here. So -2 times -3 is +6. We'll also try f prime of 0. F prime of 0 would be -2 times 0, which of course is still just 0. And then we can do f prime of +3. Well, f prime of +3 is -2 times 3, so that would be -6. And then f prime of 5, well, that'd be -2 times 5, so that would be -10. Now, the reason I put this graph here is we can actually be a bit more visual with this. It's hard to tell exactly using a graph what the slope of the tangent is, but it does give us a bit of a reference. If we look at where x is -3, that's over here, we can see that over there it's got a pretty decent upward slope. So saying the upward slope is 6, that probably makes some sense. It's like, that's pretty reasonable, right? Now, when x is 0, our derivative was 0. That's no surprise at all, because that's right the maximum point there. And at that maximum point, it's like a flat line up there. So yeah, the slope would be 0 there. That makes sense. If x was 3, we're over here. That's a pretty steep downward slope. So that makes sense that it'd be -6. And then when x is 5, it's off the charts here, but we'd be way down there. And I think you can agree it's going to be a really steep negative slope. So yeah, -10, that makes sense to me. So again, the derivative just tells you what the slope of the line is tangent to the original curve at any point x, right? So the slope can change depending on what x is, depending on your function, of course, right? All right, so here's another power rule question. This is the one that I kind of alluded to in the plan part of today as being a bit more difficult. Find the derivative of f of x equals that horrible chunky looking thing right there, right? Right as it stands right now, that looks like a fraction, and we have not learned a method for finding the derivative of a fraction yet. So we're going to have to do the next best thing. We're going to have to see if we can take this fraction and break it apart into a couple pieces. Because as we've learned with the power rule, we can take the derivative of something that is just a bunch of things added or subtracted together. So what I mean by breaking this apart is, what if we wrote this instead as f of x equals, let's just break apart the top here. So it'd be 4x to the power of 3 over x minus the fourth root of x over x. So all I did there was basically I thought, okay, since this is a fraction over x, what if we went like a step back and we just said it was a fraction with a denominator of x minus another fraction with a denominator of x, which if you actually like did this, it would give you this in the first place, right? Now, the reason that this helps me is we can actually kind of simplify these things. Now, 4x to the power 3 over x, that's not bad to simplify. That's just going to simplify down to 4x squared, because one of the x's on the top and the bottom will cancel out. As for this other one, it's a little bit more tricky. I want to remind you that a radical, a square root or a cube root, etc., that can be thought of as a fraction exponent. So this is like saying x to the power of 1 over 4. So if we're doing x to the power of 1 over 4, and we're dividing that by x, when you divide two powers with the same base, you can just subtract the exponents. So kind of like what we did here, when we went x to the power 3 divided by x, we could just subtract the exponents, so that makes it x to the power 2. We can do the same thing to the exponents here. So 1/4 minus this guy's exponent would be 1. 1/4 minus 1 would be -3/4. So we can say this is minus x to the power of -3 over 4. Now that we have it as a couple of powers, we can take the derivative of this relatively simply. So to find the derivative, we just need to find the derivative of each piece. We'll start with this first one, the derivative of 4x squared. You just drop the 2 down out in front. That would make that 8x. Knock the exponent down by 1, which makes it 8x to the power of 1. And then as for this one, its exponent will also have to drop down out in front. So this is going to be minus -3. Ooh, that's a little hard to write. -3 over 4 times x. Drop the exponent down by 1. Now remember, 1 in this case would be like 4 over 4. So if we take away 4 over 4 from this, this gives us to the power of -7 over 4. Because -3/4 minus 1 full whole is -7 over 4, right? Now we can do a little bit better to clean this up, because that still looks pretty terrifying. I kind of prefer it if you clean it up as much as you can. The 8x is fine. There's nothing wrong with that. But since there's a double negative here, we're subtracting -3/4 times this. Let's just make this plus 3/4 times this x to the power of -7 over 4. Now, a negative exponent in math, just by the way, we don't like tolerating that. It's a relatively easy thing to fix. When you have a negative exponent, it just becomes the denominator of a fraction. So this becomes 1 over, I'll be actually really specific here. I'll say x to the power of +7 over 4. But I can actually go another step further with this, because as much as we don't like having a negative exponent, we also don't like exponents to be fractions either. So I'm going to turn this back into a radical number. That's like with a root sign, right? So to clean this up one last time, we'll say this is 8x plus, let's just even write this as a single fraction. 3 times 1 is just 3 over 4 times x to the power 7 over 4 would be the fourth root of x to the power of 7. So this right here would represent the derivative of this original function. It's not the most satisfying thing to look at. It's actually pretty horrifying, to be totally honest with you, but it is accurate nevertheless. This is about as tough as these kinds of questions get, at least at this point in this course, but it is something that we might be able to, or might be expected to deal with at some point. Anyway, let's keep on going. The product rule, we're just gonna like jump right into this here today, because it is that important. We learned last class that if you have a function that is either the sum or difference of two other functions, you can just differentiate each function separately. So in other words, if you have a function that's just two things added together, you can just take the derivative of the first piece plus the derivative of the second piece. Boom, you're done, right? No big deal. With products, however, it's not quite as simple. As a matter of fact, there's kind of a really Mickey Mouse kind of formula that we have to use here. I'm going to be totally bluntly honest with you. I don't have a formula sheet in front of me, so I'm not sure if this is on your formula sheet or not. If it is, it would be found on the back page of the formula sheet, so you can always have a check for that there. But I feel like this is something I would definitely be giving you. But anyway, regardless, if you have a function h of x, like this is your original function, and you can think of that function as just something times something. It's just two things multiplied together. And then to take the derivative of your original function h of x, you just take the derivative of the first piece times the original second piece, plus the original first piece times the derivative of the second piece. It's really weird in that regard, right? So again, going over it again, if you have an original function that's just two things multiplied together, to take the derivative of that function, you take the derivative of the first piece and multiply it by the second piece just as is, plus the original first piece times the derivative of the second piece. This is a really weird one, right? It's not nearly as predictable as it would have, or as you would have seen, but it is nevertheless the rule that we have to use. And it is very convenient every now and then. I am going to be honest with you today before we do any examples. The examples we do today, you might be kind of like rolling your eyes at, because there's another way of doing them using the original power rules we've been dealing with this whole time. But I'm showing you these examples on purpose so that you can see that, yeah, that this power rule or product rule does in fact work, that it's not, just something we just kind of made up on the spot, as if we would do that. Anyway, enough of me rambling. Let me show you an example. Use the product rule, so that rule we just covered, to find the derivative of f of x equals x cubed times x squared plus 2x. So I want you to notice that this function is just something times something else. So to find the derivative of this, we'll call this f prime x. This is going to equal the derivative of the first piece. So the derivative of x cubed, which is 3x squared, times the original second piece, which is x squared plus 2x, plus the original first piece, which is x cubed, times the derivative of the second piece. Well, the derivative of x squared plus 2x would be, well, the derivative of x squared is 2x, plus the derivative of 2x, well, that would just be 2. Because think of it this way, it's like x to the power 1, so 1 drops out in front and it becomes x to the power 0, which is just 1 itself, so 2 times 1 is just 2. There it is. Awesome. Now, I do ask, of course, when you have questions like this, you should always expand them out and simplify it. So if we expand this out and simplify it, this piece is going to have to double dip through here. 3x squared times x squared would be 3x4. 3x squared times 2x would be 6x3. Plus x3 times 2x would be 2x4. And then, I guess I should have drawn the arrow there. And then x3 times 2, of course, would be 2x3. And while we're at it, why don't we just combine our like terms? 3x4 plus 2x4, well, that would be 5x4. And then 6x3 plus 2x3, well, that would be 8x3. And that function right there would represent the derivative of our original f of x. Now, kind of like I alluded to in the last slide, we could have used the power rule from last class if we just expanded the function in the beginning, right? Would it have given the same answer? Probably can guess right now, yes, it would have given the same answer, but let's prove this real quick. If we double dipped this through in the first place, and we said that the original function f of x equals x5, I guess, because x3 times x2 is x5, plus x3 times x, or 2x, is 2x4. And then if we took the derivative of that, just using our normal power rules, that would bring the 5 down out in front, so it would be 5x, and then the exponent would drop down to a 4, plus, for this guy, we'd have to take the 4 and put it down, so 4 times 2 is 8, and that would knock that down to x to the power of 3. And what do you know? That exactly matches what we did up here. As a matter of fact, right now you're probably thinking, hey, wait a minute, this second piece was easier. Why aren't we just doing that? That's way easier. You're right, it is easier. And to be totally honest with you, in a case like this, I would absolutely never use the product rule to solve that. Because, yeah, just double dipping it through and using the power rule, way easier. Takes way less time, right? However, as you might be able to guess, there are going to be some certain situations in which you have to use the product rule. You wouldn't be able to double dip something through, or if you did, it would just look like an absolute nightmare. So there is a time and a place to use the product rule. It's just another tool in your tool belt that you can be using in order to solve these kinds of problems. Anyway, we got a few more questions we'll do. Let's try this one. Use the product rule to find the derivative of y equals the square root of x times 5x to the power of 4. This is a pretty decent one actually to be using the product rule for, because if you tried to like multiply this square root x in, you're going to get like a fraction exponent, or you're going to get like a decimal exponent. It's just not as ideal, right? So let's use our product rule. the product rule is going to say that the derivative of y, so that would just be y prime, means the derivative of y, right, equals the derivative of the first piece. Now, this is what's kind of funny. The derivative of the square root of x can only be found if you think of the square root of x as x to the power of 1/2. So the derivative of that piece would be 1/2 times x to the negative 1/2, which in itself I probably want to clean up because that looks pretty gross, but we'll leave it as is right now. Multiplied by the original second piece, so 5x to the power of 4, plus the original first piece, I'll just call it the square root of x right now, just to keep it the same, multiplied by the derivative of the second piece. Well, 4 is going to come down out in front. 5 times 4 is 20, and that would make it x to the power of 3. And this kind of looks like a bit of a mess. I think this piece over here is the craziest looking thing, so I think I'll change this. Remember, we don't like having fraction exponents, and we also don't like having negative exponents. So that's kind of a 2-for-1 bad deal right there. Making it positive means we're going to basically just put this piece underneath a 1. But also the fraction exponent, like an exponent of 1/2, is just the square root of x. So not really a huge surprise on this one. This is just going to become 1 over 2 to the square root of x, or 2 times the square root of x, I should say, multiplied by 5x4. And then this guy, really, there isn't much I can do to fix that, if I'm being totally bluntly honest with you. This is just going to be the square root of x times 20x to the power of 3. Now, if you want to go a little crazier with this, we might as well write this piece as a single fraction. So you could write this as 5x to the power of 4 over 2 square root x. And then this is still plus the square root of x times 20x to the power of 3. Now, I suppose if we really, really, really wanted to go crazy with this, we also could like combine this together to make it a fraction or a decimal exponent. Because I think if you actually made these a decimal exponent, keep in mind the square root of x is like x to the power of 0.5 or 1/2 as we set up here. This is just going to make this a total grand exponent of like 3.5. And then same with over on this guy, 4 minus 1/2 is also going to be 3.5. But decimal exponents are so bad that I wouldn't even bother doing that. It's not really worth the effort. So in all honesty, I would be totally fine if you just left it at this point. But out of your own genuine curiosity, if you really, really, really wanted to continue this further, it would look like 5x to the power of 3.5 over 2 plus 20 times x to the power of 3.5. Now, 5 divided by 2 is 2.5, so we could add 2.5 to 20. So this is going to equal 22.5 times x to the power of 3.5. Now, 3.5 could also be turned into a fraction. So this could be 22.5 times x to the power of 7 over 2. And then you could just change that to 22.5 times the square root of x to the power of 7. And right there, all that work I just did there, you probably were like, what the heck? Why on earth are you doing this? What is even going on? Yeah, I wouldn't blame you, right? That's why I would personally stick with this box right here. There's nothing wrong with that answer. As messy as it looks, this guy down here certainly looks a lot like more trimmed. It's not really worth the effort to get there. So why bother, right? But it is what it is. Technically, I guess this one is more simplified, but like, let's be real here. This is good enough, right? As long as you're getting the derivative accurately and you're simplifying it down to a point where it's usable, that's pretty much all I'm really worried about there. Anyway, let's march on. So use the product rule to find the derivative of this whole thing. This would be quite a long one to double dip through if you were to do the power rule on it. Like you'd have to multiply all of this all through. It wouldn't be the end of the world by any means, but certainly this might be one that the product rule works pretty well on. Let's give this one a shot. We'll just do this one all together. So the derivative of this is going to equal the derivative of the first piece, which would be 2x minus 7, multiplied by the original second piece, x cubed plus 2x minus 8, plus the original first piece, which is x squared minus 7x, multiplied by the derivative of the second piece, which would be 3x squared plus 2. And remember that minus 8, the derivative of that would just be 0, so we can just ignore that. I'd be tempted to leave it just like this, but I can't because it's too much, right? So we would need to actually double dip this all through, at which point it's like, why didn't we just do that in the first place and use the power rule? So maybe that point I was making a second ago wasn't actually really all that good. But anyway, dipping all this through, 2x times x to the power of 3 is 2x to the power of 4. 2x times 2x is 4x squared. 2x times minus 8 is minus 16x. And then we'll deal with the 7 here. Minus 7 times x cubed is negative 7x cubed. Negative 7 times plus 2x is minus 14x. Negative 7 times minus 8 is plus 56. And that's just that first piece there. Holy smokes. All right, then plus x squared times 3x squared, well, that'd be 3x4. X squared times 2 is plus 2x squared. Negative 7x times 3x squared is negative 21x3. And then negative 7x times 2, well, that'd be negative 14x. Wow. Okay, so we got to collect our like terms. You know, I'm going to like change my pen color here just so I can actually see this for a second. So if we're going to combine all our like terms, we have 2x4 for another x4. Oh, and then 3x4. That's about it. So 2x4 plus 3x4, well, that would be 5x4. So that one's all well and good and done. Just so I don't lose myself here, I'm just going to like cross them off as I go. Let's do 3's next. So negative 7x3 minus 21x3. So negative 7 minus 21, well, that would be negative 28x3. So those guys are now gone. I didn't underline those ones, but it is what it is. You see what I'm doing. Next up, we'll do the x squareds, I guess we can do. So 4x squared plus 2x squared, well, that would be plus 6x squared. So plus 6x squared. That's gone and that's gone. And then for these ones, negative 16x minus 14x, and then minus another 14x. Well, negative 16 minus 14 is negative 30. Negative 30 minus 14 is negative 44. So that's negative 44x. Bingo, bango, bongo. Those things are gone. And then guess what? We just got that plus 56 left over. Boom. You can just settle in there. No big deal, right? So that chunky formula right there, that is the actual derivative of this f of x function here. So we could call that f prime x. That's it, right? Now, if you are again wondering, why didn't we just double dip that through in the first place? Well, it's because I told you not to, right? Literally, that's the only reason why. In all truthful honesty, I would have totally double dipped this through first. Probably would have been way easier. But hey, I was giving you the benefit of the doubt when I said, hey, maybe product rule is better on this one. I don't know. There is a time and a place for product rule. I honestly am not sold that this is the time or place, but it does come around. It is a rule we need to know, and that is what it is. So we're done. So for practice, what I'd like you to do is lesson 3 product rule worksheet in your notes booklet. Like that's your worksheet notes booklet. You'll also want to make sure that you've completed the other 2 handouts from Unit B as well. You're going to find that Unit B, the derivatives unit, really builds on itself. There's a lot of stuff that comes back that you just need to know like the back of your hand. But otherwise, it is what it is. So I'll make sure we go over this again some other day. But otherwise, best of luck.